first refine our results. And all we're going to do at no cost is we're going to use something better than Chebyshev's inequality, which is called Hovding's inequality. I'm not going to prove it here. You can find the proof in the lecture notes. It's actually a pretty standard proof, so you can find it anywhere. The proof is a bit more technical. That's why I decided not to do it. But let's look at the result. So the setting for Hovding's inequality is the following. It says, consider IID, real valued zero mean random variables xi, with the extra added assumption that the random variables here have to be bounded. Okay, so there is this assumption that these random variables belong in the set AI BI with AI less than BI. Then what you can show is that for all epsilon positive, and by the way, I assume that everything is zero mean, I'll put that here, the probability that the absolute value of 1 over n, sum from I equal 1 to n of the xi, is greater than epsilon. So there's a mean hidden here. We're looking at how far the sample mean is from 0, which is the mean. Then the bound that we have, instead of being 1 over n, as in Chebyshev's inequality, is now 2 exponential minus 2n squared epsilon squared, sum from I equal 1 to n bi minus ai squared at the denominator. So let's talk about that bound a little bit. So number one, there is an exponential behavior. There's a minus sign, and n is at the numerator, n squared actually. And so potentially that's a much, much, much faster bound. So it's telling us that just because we're using a more powerful result, we can actually prove that the concentration of the sample mean around its average is much faster. It's not polynomial or inversely polynomial, it's actually exponential. The second thing I want to highlight is it's important to know how to read that result. It looks like the behavior is exponential minus n squared, but it's not. Because the denominator here, if you look at the denominator slightly carefully, it's a sum from I equal 1 to n of bi minus ai squared. So in general, that denominator, it behaves as, formally it's called theta of n, which means it's a constant times n. So n squared divided by n is n, and therefore that behavior of the Hovding's inequality is telling you that the bound is of the form exponential minus some constant beta times n. It's still exponential, but it's not n squared. So be careful with that, that's one common mistake. So Hovding's inequality is just a refinement of Chebyshev's inequality. When you'll see the proof in the lecture notes, you will realize that it's actually based on a different boosting. Instead of using a boosting with the function x squared, we use an exponential and we optimize it a little bit. Now, with that new tool at hand, we can reproduce the exact same analysis that we did before with the change that now we can use that bound. So I will leave it to you to check that slightly carefully, but one can show that the probability that the empirical risk of a given hypothesis Hj differs from the true risk of Hj by more than epsilon is now bounded by 2 exponential minus 2n epsilon squared. So this is an application of Hovding's inequality, and just as a hint, the reason that works is because the random variables that we're looking at that are involved as xi's in the definition of the empirical risk are actually indicator functions, so they're in 0, 1. So bi is equal to 1, ai is equal to 0. So then the next step, if you remember, was to use a bound on that probability of the empirical risk of H star minus risk of H star in absolute value greater than epsilon using the union bound. We will have again a factor of m showing up. But the big difference with what we had before is that now m shows up in front of an exponential minus 2n epsilon squared. And so now if you ask for that probability to be delta, what you will see if you solve for n is that the dependence on m, the size of the hypothesis class, is completely different. Specifically now, you still get the 1 over 2 epsilon squared. But now you get a log in front of the size of the hypothesis class and delta. So this is a much, much more satisfying result. Why? Because you see that it's allowing you now suddenly to use a much more complex model and still have a reasonable number of samples. Because even if m is 1 billion, the log of 1 billion is actually not that large. So the presence of that logarithm is the only reason why there's any hope that we can actually learn complicated functions using a finite number of samples in our data set. If we didn't have that log before, learning would work, but you would need such a huge number of sample that you would be down to the point where maybe memorizing is enough. So learning actually makes sense because of that log. And to get that log, as you notice, we had to do quite some heavy lifting. The use of Hoeffding's inequality, that's not simple probability. But that's good news. We can learn. Now, M can be quite large, as I said, but with enough data, you can generalize not just a given hypothesis in the set, but actually the best hypothesis that you find by empirical risk minimization. Now, as Said was asking just a few minutes ago, how about learning H sharp, right? What we care about is not just generalizing. We'd very much like to generalize well by saying that, well, maybe it's true that H star generalizes, but we would also like H star to behave almost as well in terms of risk as H sharp, the model that minimizes the true risk. It turns out that we can actually prove such a result. And that result is based on the following lemma. The lemma says that if you can prove that for every J in your hypothesis set H, the model Hj generalizes well in the sense that the absolute value of the difference between the empirical risk and the true risk is less than epsilon, then you can show that the true risk of H star minus the true risk of H sharp in absolute value is less than 2 epsilon. So you have to introduce a factor of 2. The bound is a bit looser in a way. But in a way, it's telling you that if you can show that every model generalizes well, then indeed it's true that your minimizer of the empirical risk is actually pretty good at minimizing the true risk and gets almost the same performance as the optimal minimizer of the true risk. So let's try to establish that result together here. The result is not complicated. It's a bit astute, and you have to be tracking somewhat carefully the definitions of H star and H sharp to make a clear case. Okay? So what we're going to do is we're going to manipulate the quantity that we're after, which is the difference between the risk of H star and the risk of H sharp. So risk of H star minus the risk of H sharp. So one trick I'm going to use is I'm going to introduce the quantity that I've studied before, which was the empirical risk of H star. And the way I'm going to introduce it, I'm going to add it and subtract it. So I'm just going to rewrite that as the risk of H star, to which I subtract the empirical risk of H star. Then I compensate for that new term by adding it. And then finally, I have to remove the risk of H sharp. Then I'm going to use the fact that the absolute value satisfies the triangle inequality to upper bound this by 2 terms. The risk of H star minus the risk empirical of H star plus the absolute value of the risk empirical of H star minus the true risk of H sharp. Okay, and so I'm going to give name to these 2 terms. Oops. And I'm going to try to analyze them carefully. So this term is going to be term number 1. This term here is going to be term number 2. So let's try to analyze the first term. So what I know is that my assumption is telling me that for every J, I'm assuming that the empirical risk of the model Hj minus the true risk of the model Hj is less than or equal to epsilon. So that's the assumption that I have in my lemma. Therefore, the model that minimizes the empirical risk has to satisfy that because it is in the set. H star is one of the Hj, and therefore we can conclude that R hat n, the empirical risk of H star, minus the true risk of H star, has to be less than epsilon. That's because H star belongs to H. And so my assumption says every assumption generalizes, so H star has to generalize. So the other thing that we're going to notice is the following. By definition of H sharp, so by definition of H sharp, what do we know? H sharp is the minimizer of the true risk. So for sure, it must be that R of H sharp is less than R of H star, right? Because H star is a model in my set, but it might not be H sharp. H sharp is the one that minimizes the risk. And what I've also proved, because of this sentence I wrote before, is that the true risk of H star is no more than R hat n of H star, the empirical risk, plus epsilon. Okay, that follows from the equation I wrote just above. Now, similarly, by definition of H star, what is H star? H star is the minimizer of the empirical risk. So by definition of H star, we know that the empirical risk of H star has to be less than the empirical risk of H sharp, right? That's because H star is the one that minimizes the empirical risk. And because H sharp is a model, and I know that every model generalizes well, I know that the empirical risk of H sharp cannot be too far from the true risk of H star. Specifically, it has to be less than the true risk of H star plus epsilon. And again, the reason is because H sharp is a model, and we're assuming that all models generalize well. So if you look at what we've done, what we're really saying here is we're saying that because of the assumption that we've made, if you look at the difference between the empirical risk of H star and the true risk of H sharp, they're actually not too far away. Specifically, R hat n of H star minus R of H sharp is also going to be less than epsilon. Okay, so when you have an absolute value less than epsilon, there are two inequalities to check. You have to check that R of H sharp is less than the empirical risk of H star plus epsilon, but that's exactly what we proved in that inequality star here. And the second thing that we have to check is that R of H sharp is greater than the empirical risk of H star minus epsilon. That's exactly what we proved in that second inequality there. So the last statement is true. So putting everything together, you will get exactly the bound that we're after. So you have to backtrace our calculation, but you can convince yourself that we proved that the difference between R of H star, the true risk of H star, minus R of H sharp, the true risk of the model that minimizes the risk, is less than 2 epsilon. 1 epsilon is coming from here. That's the bound on 2, and 1 epsilon is coming from the bound on 1. Okay, so that lemma is true, right? So what we're showing is that we're showing two things. We're showing that one, H star does generalize reasonably well if you have enough samples, and enough means something that grows like logarithmically with the class size. That's good news. Two, we're showing that, well, the bound that we got was pretty loose. We had to use a union bound, but effectively, the union bound forced us to say the minimum, the H star that minimizes the empirical risk is a good bound if every model generalizes well. But what it allows us to do is it says, well, if all models generalize well, then for sure, what we obtain as empirical risk for H star is actually not too far from the true risk for H sharp. That's what the lemma here is saying. But it's not telling us how to make the risk of H sharp small. The risk of H sharp is limited by what your class H is.